Hello, in this video we are trying to determine the volume of this vegetable cut in this shape. This is the y direction, this is the x direction, this is the origin, and this height is the z direction. So y, x and z. At a constant y we have this plane here, at a constant x we have that plane there. Okay, so let us say this plane here has the equation x plus y plus z is equal to 1, and it's also bounded at the bottom by the plane of that book. Let us say that's the xy plane. So it's bounded up top by this plane, bounded at the bottom by the xy plane, on this side by the yz plane, on this side by the xz plane, and this point is the origin 0, 0, 0. Okay, we have everything. We can set up the triple integral. To determine the limits of integration, we need to freeze two coordinates. Let us freeze x and y. So we have just seen constant y is a plane like this, constant x is a plane like this. The point of intersection between those two planes will be a line like this. Anytime two planes intersect, we get a line. So to determine the limits of integration for z along that line, we need to see where the z should stop. So clearly the bottom of that book is on the top of that book, bottom of the pen is on the top of the book. So that's the xy plane. So z is equal to 0. And up top it's along this plane here. This plane has the equation x plus y plus z is equal to 1. So we can use that equation. We get z is equal to 1 minus x minus y. And we have dz, dy, dx. That's the area element. Now we need to determine the limits of integration for y. Remember, constant y is a plane like this. So how many of these pens, how should these pens should vary so that they cover this part of the plane? So clearly that is y is equal to 0 and it's stopping at this particular point. To determine this point, we should make use of this equation. This is touching the plane. I did not cut this vegetable very clearly, but it's actually touching the plane. So z is equal to 0. Now if you add a y on each side of the equation, you have y is equal to 1 minus x. So y is varying from 0. The pen is starting here, and these pens are varying from 0 till this point here, and that point has the equation 1 minus x. Okay, now we need to determine the limits of integration for x. So this is the plane here that we just saw, and these planes should start at this point and end at this point so that it covers the entire solid. So this point clearly is x is equal to 0 because that's the y-axis. Obviously x will be 0, and these planes are stopping at that point. To determine the equation for that point, clearly we can see that that point is on the x-axis, so y is equal to 0. So y is 0 and you get 1 is equal to x. X is 1. Now we can solve this. Integration of dz is z. Z varies from 0 to 1 minus x minus y. So we have 1 minus x minus y, and then the next one we have dy. So if you integrate with respect to dy, you have y minus xy minus y square over 2, and the limits of integration are 0 to 1 minus x, 1 minus x minus x, 1 minus x minus 1 minus x whole square over 2. We have 1 minus x plus x square minus x square plus 1 minus 2x over 2, 1 minus 2x plus x square minus x square over 2 minus 1 half plus 2x over 2. So we have 1 minus 2x. X square minus x square over 2 is plus x square over 2, and you have minus 1 half, and you have a plus x, and you have minus 2x. So plus x, 1 minus x plus x square over 2 minus 1 half, because 2x minus 2x plus x is minus x. Okay, now we need to integrate this with respect to dx. So we have x minus x square over 2 plus x cube over 3, so x cube over 2 minus 1 half x. I can also simplify 1 and 1 half and I would get 1 half, or I can also leave it like this. The limits of integration for x are between 0 and 1. So if you substitute them, you have 1 minus 1 half plus 1 half minus 1 half. So these two cancel. 1 minus 1 half is 1 half. I don't have to substitute 0 because all of them have an x term. So if I substitute 0, they all would vanish. So 1 half is the volume of that solid. Thank you for watching.